Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So we're going to look at this specific concept under electricity and magnetism, and this is the concept of capacitance, which basically is going to assist us try to see how various aspects of a charge distribution and the concept of electric field can be exploited to assist us perform our day-to-day functions and basically try to make devices which are of essence for us in our present day technology. So in this particular respect, we're going to look at one of these devices that is referred to as a capacitor. And we're going to see that a capacitor basically is a device that is used of course, in storing what we refer to as charges. So therefore, we're going to see later that this particular concept is going to be exploited heavily in the application of what we call electronic devices, which are gadgets that we use in our day-to-day lives. So in this specific case in electronics, we're going to see the application of capacitors in trying to, of course, store what we call the potential energy. So this is one of the applications of capacitors, this particular devices that we refer to as capacitors in storage of a potential energy. And then next we're going to see that it's going to be used out in filtering unwanted frequencies, especially in communication gadgets. And then we're going to see also that apart from that, it's going to form what we refer to as resonance circuits. And among others also, we're going to see that of course it's going to form what we refer to as a frequency dependent and independent voltage dividers. And of course, among others, we can just list a long application for this specific device that we refer to as a capacitor. And in actual sense, apart from delaying voltage changes in combination with other devices like the resistors that we're going to see later, of course, they are going to find wide application in our day-to-day life. So basically, we're going to look at the basic configuration of this specific device that we call a capacitor, and try to see how we can be able to quantify the various aspects that we have looked at insofar as charge and electric field is concerned. So I'm going to give two illustrations on the board, which are going to assist us, of course, figure out how we can be able to represent this specific device that is known as a capacitor. So the above illustration shows a basic configuration of what we refer to as a capacitor. And as we said, of course, it's used to store charges. So we'll be having this one as a positive plate and this one as a negative plate, respectively. So the field lines, electric field lines, are going to run from the positive to the negative. And then so far as this specific field lines are concerned, we're going to see that they are going to be experienced over a particular distance, which is a separation distance in these plates, which I can be able to illustrate using that particular letter L. And then, of course, in our later discussion, we're going to see that the concept of area over which these field lines are going to be expressed is going also to play a role, and therefore that is going to be part of the geometrical aspect of this specific configuration that we're going to discuss later. Now, in this second part of the illustration that I've given on the right part of the board, this is going to assist us, of course, try to create the relationship that exists between these charged plates, whereby we're going to see that, as we said, electric field lines in this specific point charges are going to emanate from the positive, of course, charge, and they're going to terminate at the negative charges, as we said in our discussion on point charge from our previous video. So I'm going just to illustrate this one using those arrows, which is indicating the vectors of those fields respectively. So in that particular case, this is the basic illustration of a capacitor. And having talked about its relevance and application, therefore I'm going to look at how we can be able to, of course, figure out different characteristics of this specific what we refer to as a capacitor. Now, as we said, this is a device that is used to store charges. And therefore this we expect that this particular device is going to be charged at a particular point, and in that particular instance, like therefore we're going to say that it's going to switch charges. And in some cases we're going to see that this particular device is going to be uncharged. And in these specific two instances for a charged capacitor and uncharged capacitor, we're going to see that the net, what we refer to as, of course, the net potential difference is going to be, or the net charge on this either charged capacitor or the uncharged one is going to be 0. And whenever this charged capacitor, of course, is in this state of what we refer to as charged, we're going to see that the positive plate is going to acquire what we refer to as a positive charge, and the negative plate is going to acquire what we refer to as a negative charge. And in this particular instance, we're going to see that the positive charge is going to experience a higher, what we refer to as a higher potential difference compared to the negative charge. And there's going to exist, of course, this what we refer to as delta V, which is going to be the magnitude of the potential difference that is going to be created between these two plates when that specific capacitor is charged. And some of the experimental data which has been collected concerning this specific concept of charge has shown that there is a relationship that exists between what we call the charge which is stored inside the capacitor and what we refer to as, of course, this specific potential difference that I've illustrated using delta V. And in any case, when we are going to consider this electric potential difference, which between these two plates, then therefore from those experimental data, we're going to see that there's a linear proportionality which is going to be experienced, whereby the charge that has been stored is going to be proportional, or is directly proportional to the potential difference that is being experienced. Therefore, from this we can be able to derive an equation which is going to give a relationship between charge and the magnitude of the potential difference that is being created between the plates, whereby this one represents the stored charge and this one represents the potential difference between the charged plates. And the constant which I've given as C is going to be the positive proportionality constant, which is going to be referred to as capacitance. So this positive proportionality constant given as C is going to be referred to as capacitance, that we have of course stated as a topic of discussion for today. Now therefore, as we had said, that capacitance is the ability of a device to store charges, electric charges, and therefore we're going to see that there is a relationship that exists between this potential difference and the capacitance that I've stated. And therefore we're going to depict this aspect of capacitance, and it's going to have as some units of measurement which we refer to as farads. And in this case, 1 farad is going to be denoted as such, and this is equivalent to 1 farad. Of course, this can have various other conversions that we're going to see, whereby 1 farad is basically equivalent to the ratio between a coulomb and what we refer to as voltage, which basically we had said is a potential difference in terms of volts. So therefore, we can be able to give that one in terms of these dimensions of 1 coulomb over volt to represent what we refer to as 1 farad. So in that specific case, I'd like us to take note of these particular differences, or rather ratios that I've mentioned for those specific units of measurement for what we refer to as a capacitance, which is measured in farads. So there are other divisions that we're going to see being exploited, like the millifarads, microfarads, and of course others which are going to be divisions, the multiple divisions of tens, which we have already looked at in our description and discussion on topics of units. So I'm going to give our last illustration for the symbols that can be used to indicate capacitors. Now, in this specific topic and discussion of electricity and magnetism, we're going to encounter various symbols which are going to assist us, of course, make it easier for us to understand electric circuits. And in this case, the concept of capacitance and the devices which are being referred to as capacitors are going to use a specific symbol to denote the presence of a capacitor in that specific circuit. So in this particular case, we're going to use this particular symbol to depict what we call a capacitor in an electrical circuit. And this basically is going to be a general symbol, but in some cases we're going to have this specific unique symbol being used to show a capacitor, which of course has been polarized. As we can see, it contains the positive and negative charge. So this implies a polarized capacitor, and of course, which is a fixed one that's going to be drawn in an electric circuit. So in this specific discussion, I hope that we have understood the concept of a capacitance and the equation that we can be able to use to represent capacitance, and the SI units that I've indicated that are going to be used in trying to, of course, give out these units of capacitance, and of course the electronic symbol that is going to be used, or a circuit symbol that is going to be used to depict this capacitance for the general symbol and the fixed polarized one that I've given on my right. So I hope that this, in collaboration with other topics on electricity, especially in our next topic of resistance, we're going to see that it's going to assist us in collaboration with this to develop symbol circuits and try to see some of their characteristics and especially their application in electronics. So that is it for now, guys. Bye. God bless you.